Hello everyone, welcome to Sustainability Modeling Lecture number 5. It's not me, it's you, or Models of Social Interaction. Let me tell you the lecture outline for today. We're going to be looking at interaction between populations, and so far in the class we've been discussing primarily single stock models. This lecture we're going to introduce a number of multiple stock models and see how these different populations interact. We're going to be doing a little bit of math for that purpose, and we'll be introducing that as well. And we're going to be looking at a first type of interaction, which is referred to as the predator-prey models. We're going to be looking at a simple example in predator-prey. We're going to be doing an advanced version of a predator-prey model. We're going to be looking at the interaction between population and catastrophes and how how a catastrophe affects population at a given point in time, and see how that changes the dynamics of the system. And then we're going to talk about another type of interaction between populations, which is epidemics, and how epidemics move over time. I think the first thing I'll say of interaction between populations, that in terms of when we speak about populations, plural, those could be different species. Could be different cohorts or simply subgroups. We're going to be doing this in the most general of senses. And the key characteristics of these interactions is that the dynamics of each population are affected by the dynamics of others. So it's a mutual interaction. And today we'll focus on several types. We're going to be looking at predator-prey interactions, which are more competition between species. We're looking at catastrophes and epidemics. So let's talk about the predator-prey interactions. A simple population interaction of the predator-prey type was derived independently by two scientists, Alfred Lotka in the United States and Lotka-Volterra in Italy, at about the same time. And the model that both of these came up with describes the dynamics of competition between two species. So these are two species competing against each other, and this essentially results in one species being able to grow at the expense of the other. Okay, and the species that is able to grow at the expense of the other we call the predator, and the one that gets grown upon or at the expense of its what we're going to be calling the prey. This model is mathematically described by a very classical set of equations that are referred to as the Lotka-Volterra equations. And I want to go briefly through them. The general idea is that we have two populations, X and Y. X is the predator population, and Y is the prey. And the dynamics, you have essentially two dynamic equations, one for the predator, one for the prey. And each of these dynamic equations has a plus and a minus term. The plus term, as we've seen before, is denoted to describe population growth, and the negative term is population decay. So in the case of the predator, the growth of the predator, it's driven by the availability of the predator and the prey, meaning basically that the more population of predator there is, the faster they grow, but also the predator needs the availability of the prey to grow. So therefore you have what we refer to these second order dynamics, and driven by this rate coefficient A. And we're going to be seeing a model of this later in this lecture, and we'll see what the numbers are. And then the predator has a natural a rate of death represented by B. So and that causes the predator to decay. So those are the dynamics, the conceptual dynamics of the predator population. The prey, on the other hand, is also able to grow, and it grows naturally, and driven by a coefficient C. And then the death or the decay of the prey, it's not only due to natural causes, but it's also due to the availability of the predator, X. That's why in the prey equation, the decay is driven by these second order dynamics. So those are essentially, that's essentially the essence of the Lotka-Volterra equations. Okay. Now, I like to rewrite these equations just to make have a better understanding of how these dynamics work. And essentially, if you just factor out a few terms, then you can recognize very easily that the first term on the right-hand side of the predator equation denotes that the growth of the predator is driven by the availability of prey. So the growth A times Y of the predator is proportional to the availability of prey Y. Okay. Similarly, in the prey, the death of the prey is driven by the population of predators. Okay, so the more predators there are available, the faster the prey will decay. Okay, so this leads to some interesting dynamics. Now, one useful aspect of looking at multiple species dynamics like this is that you can look at the concept of the equilibrium population sizes, and these are essentially, if these populations were to stabilize, what would be their values? And that they're found simply by setting the equations to 0. So basically, they don't change over time, and you can just set the right-hand sides of both equations to 0, and this allows you to calculate two values of equilibrium populations. One for the prey, y sub e, which is found as the rate b divided by the rate a, and another equilibrium population for the predator, x sub e, which is found by the ratio of constant c divided by constant d. Okay, that's some very simple, just setting to 0 the right-hand sides of the equations and solving for the population sizes. We can do a simple calculation, and let's imagine that we have a we're going to be working on this model later on in this class. Let's imagine that we have two species, foxes and rabbits, and given with these parameters, parameters A, B, C, and D, and notice the units of the parameters. A and D, which are the growth of the predator and the death of the prey, are second order units, so they have they depend on the other predator. And then B and C, which are the death rate of the predator and the growth rate of the prey, are independent, and they just have units of time. And let's imagine that we have an initial population of 100 predators, foxes, and 1,000 rabbits of prey. So let's just do that, and you can actually do a calculation, and if you do that, you can come up with equilibrium populations of, in this case, 667 rabbits and 150 foxes. So these are, if the system were to stabilize, these would be the the values of coexistence of foxes and rabbits given these dynamics. Okay. Now I'm going to fast forward. I'm going to show you some VENSIM results. We're going to come back and run the VENSIM model specifically for this case, but I did want to show you how the outcome looks like, and it's interesting that when you plot the predator and prey populations in a plot like this, you're going to see that they actually both have oscillations, and that's interesting. So the populations don't really stabilize, and this is interesting because in the population models that we discussed last lecture, where we had the carrying capacity and these concepts, essentially in all scenarios, what we saw is that the populations tended to stabilize after a while. Here, we're looking at over 1,000 years, and populations are oscillating all the time, so they go up and down. One thing that you'll notice is that they tend to oscillate around the equilibrium value. So if you look at the value for the rabbits, which was 667, it's somewhere in the middle range of the oscillations, and similarly for the foxes, the 150 population, it's in the range for the population of foxes. So that's interesting, and that happens because of this interacting dynamics of the two. Is that you're actually not able, populations don't really stabilize, but they actually oscillate over time. So if we can summarize this with a few remarks, first, there is an oscillatory behavior in both populations, and these oscillations are around these equilibrium population values. So there's really no static equilibrium. Rather, it's a dynamic equilibrium, meaning that you get the oscillations, and these oscillations are constant over time. The populations go up and down, and they do so over time. And it's interesting because this well-established classical result matches observations in many natural scenarios, and particularly when you have pure competition. And if you look at the large ecological reserves, in South Africa, or the Southern Africa, part of Africa in particular, you see that the populations of several species tend to go through these oscillations. They grow and they die, and then they grow again and die again over multiple years, when they're not intervened. So, and remember that these very simple Lotka-Volterra equations do not consider any type of intervention. No sequestering one species for food or for agriculture or anything like that. So these are really it's pure competition between two species. Okay, so we're going to be looking at this model in a lot more detail, and we're going to be looking at two versions of predator-prey models. One which is the simple case, and then we're going to be making it a little bit more complex. So that's going to be part. I'll take you through part of today's lecture. The next, the next type of interaction that we're going to be see later on in the modeling is epidemics, and epidemics are interesting, and some of the dynamics are similar to this predator-prey. The model that's used, there are a number of them, but there's a classical SIR model, SIR, for susceptible, infected, recovered model, and I want to basically flash a little bit the math here and just walk you a little bit through the equations, because we're going to be coming back to this specific example with the VENSIM model. But essentially, you have three state variables, or three control variables, which are the susceptible population, the infected population, and the recovered or recuperated population. Each of them has again a positive negative dynamic. So the positive means population is growing, and so in the case of the susceptibles, susceptibles grow as a fraction of the recovered, which means that some population that recovers from the illness can become susceptible again. Okay. And some models have this term, some don't, and I wanted to show you this one. The susceptibles decrease because of the possibility of getting infected. Okay, so once they become infected, they're no longer susceptible; they become infected population. The infected individuals grow at the expense of the susceptibles, but they can recover. Okay, so there is an ability to be recovered, and that's a negative term in the infected equation. Okay, once an infected becomes recovered, it's part of the recovery pool, the recovered pool, and the recovered pool grows according to the dynamics of the infected. Okay. The recovered grow at the expense of the infected. So that's sort of the dynamic that's captured there. And similarly to the predator-prey model, you have some alpha, beta, and gamma coefficients that are used to describe the rate of exposition to the epidemic, the rate of infection, actually catching the disease, and the rate of recovery, getting out of the disease. Okay. We're going to move on and to the next part of the lecture, which is to look at the VENSIM models. and we're going to be looking at four VENSIM models that are here. The predator-prey, and each of these models has its link, so you can actually look at the video. So I'm going to be stitching all of this together in a single video lecture, but you can actually look at the individual videos for each of these cases in YouTube, and also, of course, if you want to view them offline, the videos will also be on Dropbox. So I'll be looking at the predator-prey, simple, the advanced, the catastrophe, which I haven't really talked about because the math, it's as you will see, it's a little bit of a combination of the other two, and the epidemics, which we just explained. So that's going to take us through the next to the next part of the lecture, and so we'll lead with that.